overview of the moon. It goes through various different subtopics and just how do we learn about our closest neighbor. So, quick about the basics. What are phases? What do we see on the surface? And how do we actually study more about the moon? So, if we look at Earth, it has a diameter of about 12,800 roughly kilometers. And if you compare this to a ruler scale, it's a ruler and a bit more. That's how big the Earth is. If we look at the moon, that's about a third of Earth's diameter, or on our ruler scale, about close to 5 inches. What do you think the distance is? And we can talk about it like in ruler scales. How many rulers do you think is separating Earth from Moon? Any guesses? Yeah.
1,000?
No, it's actually a lot shorter than that. Yeah.
500?
No, it's actually one more level smaller than that. Yeah. All right, everyone.
400?
No. So actually, it's 40. Yeah. So we're actually pretty close. So it's about 385,000 kilometers, or 40 rulers. So that should probably give you an idea of how the Earth is and how how the Moon compares to it. Something about the Moon's orbit. So we know that the Earth goes around the Sun, but the Moon also goes around the Earth. So both of them, when they're kind of working together, can make things slightly a bit more complicated. So what a sidereal period is, how long it takes for the Moon to go around the Earth in one period. Yeah, that's what it is. The sidereal period is, and it takes about 27 days. So if you were to look at the Moon, say tonight, and compare it to what the background stars are, it would take 27 more days for you to get to that same point where the same stars are in the background. And that's what we call a sidereal period. The synodic period is where the Moon, how long it takes for the Moon to rotate to the same position that we're seeing on the Earth. So the next set of slides will go into phases, but if you've seen a full moon, it takes 28 more days to get back to a full moon. And the reason that these two are actually slightly different is because the Earth is also rotating, and that causes this sort of change. So they're not exactly the same period. And so because of this, and because of the two bodies moving at its own pace, it so happens that over time, over 4 billion years, the Moon has actually been tidally locked with the Earth, in that we're only seeing the same side of the same face of the Earth, of the Moon, each and every night. But not to forget that, with as many of you have seen this globe, we're only seeing one half of it, but there is the other half, and we'll get to it a few slides down. So, that's about that. About moon phases. Any idea of what, looking at this picture, what the moon phase might be at this moment? So you have the Earth over here. Yeah?
A solar eclipse?
No, it's actually not quite that. So, and we're actually also going to get, you're thinking along the same lines. We're going to get to that in a few slides. But basically, you're looking down the South Pole, and the Earth is moving counterclockwise. And you happen to have your Earth over here, Sun over there, and Moon's right there. If a person's standing at that point, what are they seeing? What half of the Moon is lit? Yeah.
Half?
Yep, but it's the half that's actually not visible from Earth. So, if you're standing here and you're looking towards the Sun, all you're seeing is the dark part of the Moon. And that means that the phase is a new moon. Oh, yeah. So you're not. Oh, go ahead.
Sorry.
That's right. So what you're seeing at that point, when the Moon is right there, is actually a new moon. So if we were to go to the next slide, the Moon is going to orbit around the Earth, and as it does, each time it gets to a particular position, it's actually going to have a different phase. So if you were out on this, if your Moon was over there, Earth is here, and the Sun is shining on this side, surely that half of the Moon is cycles, it would grow the more and more you added it. And waning is where it's kind of like decreasing. So you had full moon, and then you're starting to lose part of the face that's actually lit. So that's where you have waning on this. And then you go back to new. So pop quiz. How long does this process take?
28 days.
Right. All right, so now we had actually one of our members had suggested it might have been an eclipse. Any idea of why that's not always the case? Like if you were on new and full moon, why don't you always see an eclipse? Or let's get back to what is an eclipse? Any idea?
Is it the Earth's shadow blocking the moon?
Well, that's part of it. Yep. Okay, I'll get you to answer first.
It's when the moon is covering the sun from there.
That's the other part of it. That's right. So both of you answered it really well. On one type, we can get the moon that's between Earth and Sun. And if it's just right, the moon, when you look at it, and when you look at the eclipse, well, not directly, you find that the moon's just about covering that face of the sun. So it gets dark for a few hours, roughly. But then, on the other hand, if it's on a full moon night, what happens is the moon is now on this side, and so don't look at it. So you have the Earth's shadow that's actually falling on the moon, and that's what's causing a lunar eclipse. So the reason why this is actually not happening every single time is because of the moon's axial tilt. So the moon's orbiting around the Earth, but it's slightly tilted. Same way the Earth is also tilted. If you press an animation, the moon's tilt is about 1.5 degrees. But when you compare it to Earth's tilt, Earth has a tilt of about 23.5 degrees. So it's not that much, but there are occasions where the moon is on its orbit and it's just about right that it's blocking the sun to get a solar eclipse, or it's on the other end where it's actually getting the Earth's shadow fall on it. So that's where you have typically few lunar and solar eclipses throughout the year. The next slide will actually show you about eclipses. Okay, we went actually through this. So lunar eclipse and solar eclipse. In the case where it completely blocks it, that's called an umbral eclipse. Antumbral is where it's, like I mentioned about the distance and how just right the moon might cover it. In this case, the moon's actually slightly closer to us, and therefore it's not covering all of the sun. So you have this sort of ring, and that's what you call an annular eclipse. A partial is where it doesn't completely cover, it only covers part of the sun. So these are all cases of solar eclipses. And any idea why the moon looks red during a lunar eclipse? Yeah.
Because it's hot.
Not quite. It's actually very cold. Yeah. Second guess.
The sun is shining at it.
No, but I mean, that's true. The sun is shining on what? If it's a lunar eclipse, where is your moon relative to the sun-Earth system? In front of it or behind it?
In front of it.
Behind the Earth. So what's it getting? A shadow of? It's getting the Earth's shadow, which means that this light has to pass through the Earth's atmosphere. And that's why you're getting part of this red tinge during a lunar eclipse. All right. This is a good handy website if you ever want to know when the next solar or lunar eclipse is occurring. I believe Amanda mentioned late December.
December, I think, is the next lunar.
Yep, there is a partial lunar eclipse coming up in December.
Is there a good app out there?
Sorry?
Is there a good app for a smartphone?
I don't know. I don't have a smartphone. Probably, yeah. You can actually get, that's true actually, you could get the app to tell you what phase of the moon it is these days. So, very handy. We all love it. So now we're sort of shifting gears to see more about what we can tell about the lunar surface. So over here is a view of what we see each and every night, depending on the phase. darker ones are what we call as mare regions, but they're essentially volcanic features that have filled in to these in these spots. Now, we were looking at the near side, but this is a view of the far side. Can anyone tell me, who I've not already spoken to, what the difference is between these two views? Anything that sticks out? Yes?
One's dark and one's light.
Partially, yep. If you're, by that you mean like this one has more dark patches and this one doesn't. That's true, and actually that's one thing we don't know why it so happens to be. What we have are these volcanic regions filling into old impact basins. And the next few slides, and if you've actually walked around, there is a demo of how you form impact craters. Anyone want to quickly tell me what an impact crater is? Yes.
Crater that meteor hit.
It hit, well, partially. So we have, yep, do you want to?
An asteroid that hits the moon and creates a crater.
It hits any sort of body, but essentially that's true. So you have this space rock that comes and hits a surface, and what it does is actually excavates or removes out a lot of that material, and what ends up forming is a bowl-shaped feature. If it gets larger, that bowl shape would have certain like little peaks or rings and things like that, but that's essentially what an impact crater is. And actually, do you see this sort of feature? It's sort of dark. So in this whole bright area that is the far side, there's this sort of oval-shaped dark patch. Can people see it? Yeah. So that's what is actually the second largest impact basin in the entire solar system. That's called the South Pole Aitken Basin. It happened so early enough in the moon's history, like, well, actually part of the thing is when did it happen? But what they're trying to say is that it might have happened so early that it has effectively recorded every other impact crater in that region ever since. So it is complicated, but it's still very interesting to go and actually get a rock from there and say, how old is this feature? Because it helps us. Actually, you could move a few slides. Pause that thought. Impact craters are actually a very common feature throughout the solar system. We're seeing these pictures show you impact craters in various bodies. Earth has some. Another slide actually shows you how distributed they are. But it's such a common feature that we're still trying to, like, we have evidence of it. We're trying to understand it, how it forms, how it quickly it actually distributes the materials. So that's why the moon is one of the best examples to study impact craters. It's just because it's recording all of those through time. All right, I'll skip these. It's just, this one was just going to show you on the moon a very simple crater. It's typically that scale. That's the diameter, but on Earth it's slightly different. And this is for more of the complex craters where you have this additional features, but again, on the moon they have different diameter sizes than on Earth. So as I was mentioning about the South Pole Aitken Basin, understanding how this basin formed helps us actually understand many different things. How giant basins form. This one is about, if you look at the diameter, it's roughly 2,100 kilometers. So impact craters can go from a few meters to many thousands of kilometers in size. So yeah, it also helps us understand about what there maybe this period that we don't know much about. We need to get better age dates for certain features to know if this actually happened or not. But basically, how quickly did impact craters form? Were they actually were they just happening randomly in time, or was there an actual phase where there was more bombardment happening?
So was that like, what's the youngest crater that,
Still a stupid point, happens to answer.
So like,
Craters are still forming today, so there would be very young ones that have happened recently. Right, so,
there ever a point where you see an asteroid coming and you're like, okay, it's going to crash into the moon type thing?
We've never seen that.
Oh, okay.
No, we've never seen that. It would be interesting.
Yeah. Okay, so that was about the South Pole 18 basin. So pretty much on either side of the moon, we're seeing a lot of impact craters. They're young, fresh, or they can be really old and really weathered, and not showing their sort of typical characteristics that easily. This one is one of my favorites. It's orientally. It's called the Bullseye Crater just because the widest bit is about 900 kilometers, and it has this volcanic patch right in the center. You can actually see part of it each night. It's like half of it is on the near side, half is on the far side. So you can tonight maybe you might be able to see it. It's one of the larger impact craters that have multiple rings. All right. So a lot of what we've studied. Oh, sorry. Was there a question?
No, it's just
Oh.
the mosquito running around. Sorry.
Want to learn about the moon. So a lot of what we've learned up to now, and I mean even it's ongoing, has been through largely about the moon has been through the Apollo missions. They've collected a few hundred or 100 kilograms of rocks that they're looking through, and even then that's only from a small area of the moon. But a lot of what we understand about the rock types, the history, the impact processes comes from those sets of rocks. However, the next slide shows you other ways we study about the moon. Okay, this is not the exact one, but remember there on this table, for those who haven't seen, we have examples of meteorites. There are some lunar ones, a Martian one, but essentially that's another way we can learn about another planetary body, is to look at the rocks from that body. This is an example of a lunar meteorite that was found in Antarctica. Another way that a lot of us are currently using, since we haven't gone back to the moon to actually grab samples, is what we call remote sensing, where you send a satellite and it's orbiting around the moon, and in many cases it's taking black and white pictures and just sort of scanning the whole planet and creating a photo portrait of it. We use this electromagnetic spectrum to determine what sort of composition details can be gotten, things like that. So the next slide shows you the most recent high-resolution instruments. We're not going to tell a whole lot because I think Phil's going to cover most of it. But this is, over the last 3 or 4 years, we've had so many various missions from different space agencies throughout the world that have sent spacecrafts and that are orbiting the Earth, the moon, and have taken really high-resolution pictures of the surface. We're getting some in color data that's just telling us how the minerals are distributed through the surface, but then some are just black and white, like really high-resolution pictures. So something like this table might be actually captured just because of the high detail on those instruments. So I think I'm pretty much done. So basically from these different methods, a lot of what we're learning for the moon is distribution of shock materials from an impact event, the volcanic history, trying to piece out what the geologic history of each area is, and it can also in some ways, if we know that, help us plan in future human explorations if we go to the moon, and we will. And the last thing that I want to talk about is, apart from those data which are so valuable, we also have another aspect that we can use to study impact So one's in India and the other one is in Labrador. And interestingly, we just had a mission that went, we simulated a lunar mission of sending astronauts and a rover to a lunar environment and actually ran the mission of where would you go and what sort of rocks would you see, collect, why would you want to analyze. And we did that sort of simulation just in late August, and that's at this location called Mistastin, or Kamistastin. It is an impact crater. Some of our rocks that we have over here are from that location. And if you want to know more about how that event happened and what went on, we do have a blog that's now filled up with gallery pictures and everything. And the next slide actually tells you where that location is. So we had our astronauts, we had a rover, and we were doing a lot of geology of things and simulating a lunar event. If we were to go land on the moon, where would we go? Why would we go? How interesting is that? So I have a feeling. Last thing. I think I might have mentioned it to someone in the room, but a lot of ways that the public can get involved in all of this research and interesting features of explaining what's happening on the moon is through Moonzoo. Moonzoo is a website where it's just like Galaxy Zoo, which I haven't really played around with a lot, but it's essentially you sign up, you have a login and things, and they give you a random picture from this high resolution data sets that we now have, and you can essentially just help them identify what are crater features or what are boulder features, because they want to do a little catalog to help better understand processes on the moon's surface. So this is one way definitely that the public can get involved. There are other slides later about the various data sets, and I mean, we can have this available for those who are interested. And I have a feeling with that, I will just leave up our links and say thank you for listening, and this hopefully was a good overview of the moon.